one thing that kind of ties the periodic table to what you should know about an atom to atomic structure, so I'm going to kind of link these three together, is the number of valence electrons in an atom. And our number of valence electrons is going to indicate the electrons that are on the outer shell or the outside of an atom. So we have our nucleus in the center and then an electron cloud. And those electrons are arranged within that cloud by which ones are closer to the nucleus or further away. The closer to the nucleus they are, the lower in energy they are, the more favorable that is. So electrons will try to be as close as they can, but once it's too crowded, they'll be further away. Well, when two atoms interact with one another, they are going to come up to one another with those outer sphere or outside electrons touching one another. And so that's where all the interesting chemistry comes from, is how many electrons are out there on the edges of the atom. And we track that as valence electrons. And for nonmetals, or actually for metals and nonmetals alike, sorry, we'll just do this together. It's the number of the group number that tells you the total number of electrons that are the valence electrons. So if it's sodium in group 1, that's the columns. One valence electron. If it is carbon, which is in the 4th main group elements, it'll have 4 valence electrons. And this just works for our main group elements only. And that means the first 2 columns, seems like this should actually be over closer to the periodic table. So that's the first 2 columns and the last 6. So not the transition metals or the lanthanides or the actinides. So that kind of covers what we'll be doing with the periodic table, the atom and atomic structure. From there, then we kind of focus on this nucleus and we connect it to nuclear chemistry and what can occur when the nucleus of an atom isn't stable. So for any element, we've talked about there will be multiple isotopes. Some isotopes are stable and they don't change, and others are unstable. The ratio of protons to neutrons dictates that stability. And we won't predict which ones will or will not be stable, but we will look at what happens when they are unstable. So nuclear chemistry is going to look at a few radioactive particles, and there's more than what we cover in this class, but these are kind of a good foundation. We'll have alpha particles. These are a helium nucleus, essentially. There's 2 protons and 2 neutrons. Beta particles, which are essentially an electron. It's a negative charge with very little mass. And a positron, which is a positive charge with very little mass. So it's like the opposite of an electron. So these are the 3 main ones we'll be doing, we'll be working with. There's also gamma radiation, which accompanies different types of radioactive decay. Sometimes it happens all on its own, but it's just a burst of energy, so it doesn't have any mass. So we'll use the top 3 more. And what we're doing in this section of the chapter is we're looking at nuclear decay equations. And half-lives. So with our nuclear decay equations, we're always going to have the same format. We're going to have an isotope decaying to a new isotope plus a radioactive particle. So we always have to have one on the left side, two things on the right side, and we have an arrow that separates them. And this really becomes our before and our after. So the radioactive particles that we could see that would be emitted from the nucleus are the ones up here that we just talked about. Our unstable nucleus will then decay into a new one. And so the element itself might change, or the isotope of an element. So an example of this would be, let's do, I'm making this one up, so I don't actually know if this is how this decays. Let's do carbon-14, and I can't actually remember if it's beta or positron decay. And let's say it decays by, let's just do alpha decay. That means that we're going to make some new nucleus, and we're going to have an alpha particle leave the nucleus. So I need my right-hand side of the equation to equal my left-hand side. And we're looking at atomic number, or the charge of the nucleus, and the mass number, which is the protons plus the neutrons. So if I'm losing a charge of 2, I'm really losing 2 protons from that nucleus, meaning I'll have 4 protons left in my new nucleus. And if I'm losing a mass of 4, I'm losing 2 protons and 2 neutrons. So I'll have a total mass of my new nucleus of 10. And that is going to give us, look at a periodic table real fast. So that 4 is going to correspond to beryllium right here. I love this periodic table. It's the dynamic periodic table online. It's a great one. So that means we'll put an element symbol of Be here to show our new nucleus. And that's what our decay equations will all look like. All right, so then let's look at the half-life. We're not going to get into the equations that you would use for half-life because we don't have high enough math prereq for this class. So we're going to look at half-lives in a very simplified way. We are first going to define it. So a half-life is the amount of time it takes half of the material to change. It's a way to describe changes that happen logarithmically. So in this case, so a half-life is going to be, if I have 100 grams, the amount of time it takes to decay to half of that. Or if I have any amount of sample, it's going to be the amount that it decays by 50%. So we will look at one half-life. So let's look at the number of half-lives and the percent that remains. So when we've had one half-life, we'll have 50% remaining. After a second half-life, we'll have 25% remaining. Third half-life, we'll have 12.5. Fourth half-life, we'll have 6.25% remaining. Fifth half-life, we'll have 3.125% remaining, and so on. We won't go past 5 half-lives. And the way that you can determine the total amount of time is if 2 half-lives pass, then you would, like if you go from, let's say, or let's do 3. Let's do 100 grams of something decays all the way to 12.5 grams. We know we've decayed this to 12.5%. We've undergone 3 half-lives. The amount of time that that takes is just going to be that 3 times the actual half-life. If that's like a minute, then it'll be 3 minutes. So we're going to solve these problems in kind of an estimation, or we're not going to plug into an equation, which can be a little bit challenging when it comes to half-lives. It's important to remember that the amount of time adds. So if you're at 2 half-lives, your amount of time total should be twice as much as the half-life value. We don't divide the half-life value by half to determine the amount of time. All right, and that is my overview of Chemistry 121's chapters 2 and 10 that we're covering. I think some notable things to note are you're not responsible for electron configurations, though they're worth learning about. You're not responsible for measurements of radiation. Or the fusion or fission part of chapter 10.